Hey there, folks. Welcome back to our explainable AI adventure. Today, we're switching gears to logistic regression, and we'll be working with the Pima Indians diabetes dataset, a classic in the data science world. I'm running this in Google Colab, breaking it into bite-sized code blocks for you to follow. We'll load up the data, clean it up, train a logistic regression model with Interpret, and then dive into those awesome local and global explanations to figure out what's predicting diabetes. Buckle up, this is going to be a fun ride. Let's kick things off by setting up our toolkit. In Colab, I start with pip3 install interpret to snag the interpret library, our ticket to XAI goodness. Then, I pull in some heavy hitters, pandas for data handling, interprets logistic regression from the Glassbox module, and Sklearn tools like train test split, accuracy score, confusion matrix, and classification report. I also set up inline visualizations with set visualize provider and inline provider, perfect for Colab. Now, the dataset. I grab it from a URL hosted by Jason Brownlee, loading it into a pandas data frame with column names like pregnancies, glucose, and outcome. A quick dataset.head shows us the first few rows, pregnancies at 6, glucose at 148, and outcome as 1 for diabetes. It's raw and ready. Let's dig in. Before we jump into modeling, we've got to check our data's pulse. I run dataset.isna.sum to count missing values, and it's all zeros. No gaps here. A call to dataset.info reveals 768 rows and 9 columns, with types like int64 for age and float64 for BMI. All numeric, no categories to encode. But here's a twist. Some zeros in this dataset don't make sense, like glucose or blood pressure at 0. I check with dataset equals 0.sum, and wow, 374 zeros in insulin, 227 in skin thickness. For columns where zeros unrealistic, glucose, blood pressure, skin thickness, insulin, and BMI, I replace those zeros with the column mean using a handy loop and replace. Now our data is in fighting shape. Time to split and train. All right, let's carve up the data set. I set X as all columns except outcome. That's our features, and Y is outcome, where 1 means diabetes and 0 means no diabetes. With train test split, I allocate 20% to testing and 80% to training, keeping random state at 42 for reproducibility. Next, I fire up logistic regression from Interpret, setting its random state to 42 too. I train it with logregmodel.fit on xtrain and ytrain, then predict on xtest. How we do? Accuracy score gives us 0.78 to 78% correct. The confusion matrix shows 84 true negatives, 36 true positives, 15 false positives, and 19 false negatives. The classification report adds detail. Precision of 0.82 for class 0, 0.71 for class 1. Solid start, but let's peel back the layers with XAI. Here's where the magic happens. Local explanations. I use logregmodel.explainLocal on the first 5 test samples. For the first one, it predicts 0, no diabetes, matching the true label of 0. Breaking it down, glucose contributes a massive 3.3867, BMI adds 3.1477, age gives 1.3911, and diabetes pedigree function chips in 0.706. These push toward diabetes. But blood pressure pulls back with negative 1.4232, insulin with negative 0.3778, and skin thickness with negative 0.1397. Pregnancies adds a positive 0.429. The graph on screen is a bar chart. Orange bars for glucose, BMI, age, diabetes pedigree function, and pregnancies stretch right, favoring diabetes, while blue bars for blood pressure, insulin, and skin thickness go left, resisting it. This is XAI in action, showing us exactly why this prediction landed at 0. Let's zoom out to the global view with logregmodel.explainGlobal. This reveals feature importance across all predictions. Diabetes pedigree function tops the list at 1.6413. Huge impact. BMI follows at 0.0926. Pregnancies at 0.0715. glucose at 0.0346, and age at 0.0324, all positive. On the flip side, blood pressure is negative 0.0245, skin thickness negative 0.0042, and insulin negative 0.002, small but negative pulse. The graph you're seeing is a horizontal bar chart. Orange bars for diabetes pedigree function, BMI, pregnancies, glucose, and age extend right, boosting the odds of diabetes, while blue bars for blood pressure, skin thickness, and insulin nudge left, tempering that risk. It's a clear snapshot of what drives this model globally. What's the big deal with all this? Locally, we saw glucose and BMI dominating that first prediction. Over 6 combined contribution. That's a patient with high glucose and BMI leaning toward diabetes, but blood pressure pulled it back just enough. Globally, diabetes pedigree function at 1.6413 screams family history matters a lot. Imagine you're a doctor. This isn't just a yes or no answer. It's a why. Could tweaking insulin measurements improve this? Does blood pressure's negative role surprise us? With Interpret, we're not in the dark. We're informed. These visuals are gold for explaining to colleagues or patients. And in Colab, I'm showing them with the show function. Though you could save them too. Let's tie it all together. We took the diabetes dataset, scrubbed those pesky zeros, built a logistic regression model hitting 78% accuracy, and then used Interpret to crack it open. Local explanations gave us a front row seat to one prediction story: glucose and BMI versus blood pressure in a tug of war. Global explanations painted the bigger picture. Family history and BMI lead the charge. This is explainable AI at its finest, turning predictions into understanding. I hope you're loving this journey as much as I am. Plenty more to explore ahead. Catch you in the next one, friends.